Right, so remember before in the last lesson we said there's three important things in electricity or electric circuits. The one is potential difference or voltage, the next one is current, and the last one is resistance. Right, so now we're moving on to current. Now current is basically just the flow of charge in an electric circuit. Remember we said before you have a cell or battery that provides chemical energy to the cell, and then the charge flows throughout the entire circuit. So that flow of charge is actually current. Right, so current is the flow of charge, and together with the potential difference or voltage, it helps to produce electricity. Right, so let's look at an actual definition of current. Current or electric current, it means the rate at which charge flows. Now every time you hear the word rate means how fast or slow something is happening. It's almost like speed. So when you see the word rate in chemistry or physics, it means per time, and when you see the word per, it means something is divided by time. So rate basically means something is divided by time, okay, and it's dependent on time. So since electric current is the rate at which charge flows, it means it's charge that is dependent on time. So electric current depends on both time and charge. So basically it's like saying charge divided by time, because rate means something divided by time, and in this case it's charge. Right, so the actual formula for current is I is equals to capital letter Q over change in time. Right, let's look at what each of these quantities mean. Now I stands for current, okay, and current is measured in something which we call amps or even amperes, and the symbol for amps is capital letter A. So basically we always measuring current with a capital letter A. Then you have capital letter Q, which is charge, and charge we did before with potential difference. It's measured in coulombs, which is capital letter C, and then you have divided by this triangle and a small letter T. Now the triangle, I don't know if you have seen it before, but also in physics and chemistry, if you see this triangle, it means change. Right, so the triangle means you're changing something. And when I say change, I mean how much something has changed from the beginning until the end. And the end, we call it the final, and the beginning, we call it the initial. So change means you're taking the final minus the initial of that thing. Right, so let's go back here. So you see you have change in time. So T is time, and time is measured in seconds. So because we have this triangle, it means the change in time. So it means the final time minus the initial time. So it's the time that you have afterwards minus the time that you had before. Right, so from this formula, you can work out current, you can also work out charge, and you can also work out time. But the symbols are very important. You have to know that current is in amps. So if it is in something like milliamps, you have to change it to amps. Charge is always coulombs, and time is always seconds. So if you have time in hours or time in minutes, you have to convert that time to seconds. And again, that triangle means change, which always means final minus initial. Right, now before we did potential difference or voltage, and we said the way that you measure voltage is using a voltmeter, and we said that voltmeters are always connected in parallel, which means you have to have a branch with it. Now current is like the opposite of voltage. So current is measured using an ammeter, so that's the piece of equipment that measures current. And instead of a voltmeter being connected in parallel, an ammeter, which is used to measure current, is always connected in series, which means you can have an ammeter anywhere in the cell. You don't need to have a specific branch for it. It's just anywhere in the electric circuit. And we said before also, current also always flows from positive to negative terminal of the cell or battery, and we call that conventional current. Right, now we're going to revise some of last year's work, which I told you to just check from last year. Right, so again, we did voltage and how it changes in parallel and in series. Now we're moving on to how current changes in parallel and series. And you'll see that current actually does the opposite to whatever voltage does. So remember we said in series, voltage is divided, and if you add all of the voltage, you will get the total voltage. But now, if you're dealing with current in series, it's actually the opposite. So current in series is actually the same everywhere, which is also equal to the total current. So in a series circuit, you're going to have total current, but anywhere in that circuit, you're going to have current equal to that total current because it's the same everywhere. So in a series circuit, the current is equal everywhere, and because it's equal everywhere, it means every bulb or resistor that you have in that circuit will have equal brightness. Okay, right, let's move on to current in parallel. And before we're done, voltage in parallel, and we said voltage in parallel is the same everywhere, but now when we're dealing with current in parallel, current is actually divided, and when you add all of that current, you get the total current. And because current is divided in a parallel circuit, we call it current dividers, because you're actually dividing the total current into different amounts. Right, so just remember, in series, current is the same everywhere. If you have any current, that will be the total current, and in parallel, current is divided, and if you want to get the total current, you have to add it together. Right, so let's look at page 118 of your textbook, and let's see how that actually looks in real life. So here you have a series circuit on the left hand side, and it's a series circuit because you can see there is no branches at all, which means it's series. So since in a series circuit we said current is the same everywhere, which means it's the total current. Now if you look at the circuit here, can you see you have 3 emitters and they're all in series. You don't have any branches. The emitters are just anywhere in the circuit. So you have A1, A2 and A3, and they're all in series, and they all have to be equal to each other, and therefore you can see that they all have the value of 0.2 amps. A2 is also 0.2 amps, A3 is also 0.2 amps. So because it's series, every emitter has the same reading because the current is the same everywhere, and each of them give you the total current. So A1 is giving you 0.2 amps, which is total current. A2 is also giving you 0.2, which is the total, and A3 is also giving you the total current. Now let's look at a parallel circuit and see how that is actually the opposite. Now if you're looking at this one on the right, can you see it's parallel because the light bulbs are actually in branches. They're not just one circuit which all just flows to each other. Now if you look at this one here, can you see again you have 3 emitters. Here's A1, A2 and A3. Now if you look at A1, can you see that A1 is in series? It's not connected to any light bulb on a branch. So A1, this one here is the series one, and since they said current in series is the total current, it means A1 is giving us the total current, which is 0.3 amps. Okay, now if you're looking at A2 and A3, this one is connected with light bulbs that are in parallel because they are on branches, and we said in parallel current is divided, and if you add all, you will get the total current. So since those 2 light bulbs are in parallel, it means the total current, which is A1, 0.3 amps, is going to be divided amongst A2 and A3. So they took that 0.3 amps, and can you see A2 got half of that? It got 0.15 amps, and A3 also got half, which is 0.15 amps. So we took this total current, we divided it amongst these 2 light bulbs, and if we add 0.15 and 0.15 amps, that will give us the total current, which is 0.3 amps. Right, so can you see how that is different from series? In series, it's the same everywhere, which is total current. In parallel, this one is the total current because this one is in series. These 2 are connected in parallel with this light bulbs, so it's divided, and when we add that, we get the total current. And in this case, it's showing that this 0.3 amps is divided equally, but it's not always the case where you have current being divided equally. Sometimes it can have one less and one more. It just depends, and we will see that later on. Right, so now that you know what current is, it is the rate at which charge flows, and it depends on both time and charge, and it's equal to I is equals to Q over change in time. Now we can actually do a calculation to see, just as an example. Right, so let's go to example 3, which is on page 117 of your textbook. Right, it says here, we're just going to do number 1. A bulb requires 0.25 amps to shine brightly. Now if you see amps, it means we're talking about current. So they're telling us that the bulb needs 0.25 amps of current. Right, number 1, what amount of charge moves through the bulb after it has been on for 10 minutes? So they're asking us for the amount of charge, and they're telling us this light bulb has been on for 10 minutes. So basically, this 10 minutes is showing us time. This 0.25 amps is the current, and they're asking us for charge. So there's only one formula that you can use, which is this one here. I is equals to Q over change in time. And since they're asking us for charge, we can make charge the subject of the formula. So we can say, rearrange the formula, and then we'll get Q is equals to I times change in time. Right, then all we have to do, it's the same like the potential difference one. All you have to do is just substitute what they gave you and then solve for whatever they're asking you for. Right, so current, they said here it's 0.25 amps and it's in amps, which is what we want it to be in. So we're just going to substitute 0.25. And then they said time is 10 minutes. Now, remember we said time is always in seconds, and you can never have time in minutes or hours. You need to always convert it to seconds. So whatever time they give you, you need to make sure you put it in seconds. So the way that you do that is, you know that 1 minute is 60 seconds, isn't it? So if you have 10 minutes, all you're going to do is say 10 times 60. So just remember, 1 minute is 60 seconds. And if you have 10 minutes, it's going to be 10 times 60 seconds. So if you want to go from minutes to seconds, you just multiply it by 60. Right, so that will give you 600 seconds altogether. So you're going to put 600 seconds in this equation, and that will give you an answer of 150 coulombs. And charge is always measured in coulombs, which is capital letter C. And just remember, you always have to have units in every answer that you give. Right, so it's simple. All you do is you use the formula, substitute what they give you, make sure everything is in the correct units, which is mostly time that you're going to have to convert to seconds, and then solve for whatever they're looking for, whatever you're looking for, and that's it.